Professor Carlo De Falco. So Professor De Falco got his PhD in 2006 in applied mathematics at the Milan University. Then lately in 2018, he became associate professor at Polytechnic of Milan. He's mostly working on semiconductor device modeling and simulation, electrical circuit simulation, NURBS-based isoparametric discretization of PDE for fluid dynamics and elasticity. Let me see if...
So I activated the audio. I am activating a video just to say hello, but it doesn't really work correctly. And I should now share the screen. Let's see if it works. Why does it want me to leave? So I hope you see my screen now.
Yes. Yes, I do.
Okay. So I'll remove the background, which was annoying. So hello, everyone. Thank you, Walter, for inviting me to give this talk. As Walter said, my background is mainly on semiconductor simulations, and the application of the methods I'm going to present right now is in particular to organic semiconductors. I understand this might be a little bit off with regards to the common experience of the audience. I will try on the one hand to convince you that it does make sense to include this talk in this series of seminars. And I will also give a short introduction on the physical models, because I will not assume that any of the topics are known. Of course, I will try to keep this as short, as simple as possible, but I'm open to any more details that anyone might request from me. So, so this is the outline of the talk. I will justify the interest of the simulation of organic semiconductors because, well, you probably have heard about these materials, but I'm not sure how familiar you are with them. Then I will introduce the mathematical models, which are slightly different to what is usually presented in the other seminars of this series. And then I will introduce the interesting parts of the discretization of the equations, and the most important part, the most innovative contribution of this work, which is the adaptive mesh refinement with the hierarchical quad-tree meshes. This will be presented in 2D because for the application I'm talking about today, this is the most interesting case, but everything works in 3D, and it's our interest together with Walter, especially to apply the same methods to Poisson-Boltzmann modeling. This is common work with Pasquale Africa from MOX, who was a PhD student at the time that he did this work, and Professor Perotto, which is an expert in mesh adaptivity, Dr. Caironi from IIT at Polimi, and Professor Natali from the Department of Electronics and Bioengineering of Polytechnic. So what are organic semiconductors? So the most commonly used semiconductors, which we find in most used electronic devices, are crystalline inorganic materials, especially silicon or other compound semiconductors, which are crystalline in structure and inorganic. The use of polymers or small organic molecules as a substitute for this material has the advantage of cheaper production, as these materials can be printed with the laser jet printing, just like any sort of ink, and they can be printed on flexible substrates, unlike inorganic semiconductors. So in many applications, such as wearables or thin films that can be transparent and therefore placed on windows or any textile, they have a large advantage with respect of existing materials. Well, this is some logos of existing application, and this is particularly interesting because it's ongoing at Politecnico, or actually in a spin-off of Politecnico, which is the smart labels, which can be placed on products and have the logic and the energy source integrated in them, and are flexible and can be just glued to any material. The most common application, which we're probably familiar with nowadays, because it's being advertised a lot on TV, is that of flexible screens for portable terminals. And of course, I will not name the brand, but I'm sure you have seen these kind of devices. So this just to say that even if it's not an application you're now let's go into more details of the challenges this kind of application poses to the simulation we need to run. So the basic device in all the basic element in all electronic circuits is the FET transistor, and in particular this is the geometry of an organic thin film transistor. So this is this consists of two thin films of different materials, a semiconductor and an insulator. These are usually, in our case, both polymers, and three conducting electrodes, which are called source, drain, and gate. And by changing the voltage at the gate, one can control the conductivity of the semiconductor and close or open the electrical connection between the source and the drain. So from the electrostatics perspective, what characteristic does this device have? Well, you can see the geometry, the exterior geometry of the object is very simple, and even inside it's mainly made of planar thin films or rectangle contacts. So the geometry is in principle very simple. The permittivity is discontinuous among the different materials. But the main issue is that the charge distribution within the device and the electric potential display very steep layers, and that these layers are at locations that are not known a priori and that move depending on how the device is operated. So you can see these large jumps in this case, this is the electric potential, which occur at locations that are not known a priori and move during the simulation depending on how the device is operated. So this will justify later choices that we make about the algorithm we use to simulate these devices. And you also see that the current distribution in the device is need to be resolved correctly in order to accurately simulate the behavior of the device. So after this very, very short introduction on the physics of the device, let's move to the equations. So the general form of the equations used to simulate the current and charge distribution into this device consists of the so-called drift diffusion system of equations, the first one. but this is coupled with a continuity equation which enforces the conservation of charge, and it's time dependent in principle. And also we assume in this simplified presentation there is no charge in the insulator. This is not actually true, and it's an approximation that can be relaxed, but discussing the insulator correctly would really require too much time. I'm open to questions on that. Now, the drift diffusion name depends on the fact that the current is modeled as proportional to the gradient of the electrochemical potential phi n, and this electrochemical potential phi n can be related to the density of charge and the electrostatic potential itself. And this is the kind of relations that we have between the density of charge. So we assume for the simplicity that we only have negative, but again, I'm trying to simplify. And we have a constitutive relation that relates this density to the electrostatic potential phi and the quasi-Fermi or electrochemical potential phi n. And this is slightly more complex than in usual Poisson-Boltzmann simulations, because it's an integral relation, not a simple algebraic relation, but you can see this as a substitute for the in the Poisson-Boltzmann model. This integral includes important parameter, which is the disorder level of the disorder sigma, which is the width of the density of states, which are the states available for electrons to occupy in, well, let's say the conduction band. This is not really the case, but let's simplify it like this. So with this relation, we can manipulate the definition for the current density and represent it in the drift diffusion form finally. And this drift diffusion form as a diffusion coefficient, which is not proportional to the mobility. The proportionality between the mobility and the diffusion coefficient is known as the Einstein relation, and this does not hold in the commonly known sense in this sort of material. Instead, we have a generalization of this relation, which we call the generalized Einstein relation. And this is the expression, the relation between diffusion and mobility in this case. And this derivative here is the derivative of that very complicated integral relation that we have seen previously. And it's one of the challenges to compute this in this model. And of course, also the mobility depends on density of charge and on the electric field, so gradient of the electrostatic potential. So this is a smooth relation usually. It's modeled in different ways. The most common is the extended Gaussian disorder model. But even if this relation is smooth, as we have seen in the 2D pictures before, the density of charges and the electric field display very steep changes within the device. So even if this coefficient is not discontinuous, it is effectively discontinuous because it changes a lot in a very small range of space distance. So this is to justify that our numerical method will have to deal with the currents that do not respect the Einstein relation. So this is the first requirement, and still be thermodynamically consistent in the sense that I will explain later. We also need to be able to preserve positivity of the charge density, which is non-trivial in this case. And we need to be able to resolve the steep changes in the variables and discontinuous coefficients or almost discontinuous coefficients within the domain. Of course, also boundary conditions play a role, but I don't think we have time to go into details of that. Just to bring the presentation more closer to the general topics of this series of seminar, we consider the case where the device we are simulating is held at equilibrium. So in some way, we enforce that current is zero in this linear Poisson equation, but rather than the simple algebraic relation between the density of charge and the electrostatic potential, we have a quite complicated generalized integral formula to solve and couple to this Poisson equation. So this is a Poisson-Fermi equation with a complicated density of states function. And by the way, we need to solve this equation also in the frequency domain, linearizing around different equilibrium states. So our method needs to deal with time transient simulation, nonlinear Poisson for the equilibrium regime, and frequency dependent, linearized frequency domain simulations. So now that I have introduced the model and explained the requirements that this system of equations poses on our numerical method, let's go to define finally the numerical method. So to introduce the choice of the numerical method, I think it's useful to see where it comes from. So for the simple case, for inorganic semiconductors, and in the stationary but not an equilibrium regime, this is the equation that needs to be solved in addition to the Poisson. So the divergence of the current is zero, and the current can be expressed in the drift diffusion form with coefficient D, which is the same for both the diffusion and drift currents. So this is the Einstein relation that can be exploited for standard numerical methods. With this particular ansatz for the current, one can make a change of variables, and applying the primal mix formulation and the Galerkin method, one can present the phase discretized equation in this form, where psi and tau h are test functions, and by static condensation, which means locally solving the second equation in each element, one can eliminate it, and one ends up with a simple expression for the numerical fluxes on the sides of a mesh or between nodes of a 1D discretization. And this discretization, where BE represents the Bernoulli function, has the important property that it is thermodynamically consistent, meaning that if the electrochemical potential is constant, the current is exactly zero. Achieving the same property for the case where the Einstein relation is not satisfied is a challenge which is treated in many recent works in literature. I'm not going into the details, but I'm open to questions later if you are interested. Our approach is to represent the to solve this inconsistency is to represent the deviation from the Einstein relation by a correction potential psi that we just add to phi. And then the same numerical representation for the current fluxes can be used, and the same well-known Scharfetter-GUMMEL method can be applied to this extended Einstein relation materials as it was to standard silicon. I hope this was not too far-fetched to assume to simplify this very complex topic in so few slides. Please ask questions later if you are interested. Well, with these numerical fluxes, we first perform 1D simulation, and the purpose of these 1D simulations is to determine fit the parameters in the model to experimental data. And this explains why we need both stationary frequency regime and transient simulation, because we can use stationary regime capacitance voltage measurements, static regime current voltage measurements, and to fit the parameters, and then validate the results by comparing the frequency domain change of the capacitance with experimental data. So this is why we need to perform all these different kinds of simulation, not just stationary and transient. And here you see how we compare simulated and measured capacitance of a FET device and use the simulation to fit the width of the density of states, and then how we use IV measurements. This is the so-called trans characteristics of the device to fit the mobility and injection barrier of the device. And finally, we, after fitting the parameters, we simulate the frequency dependence of the capacitance and compare to measurements, and we find a very good match between the two. Now, 1D simulations are definitely not the interest for exascale simulation, so let's move on to the interesting part. So if I justified in the beginning the need for a multi-dimensional simulation, if we need multi-dimensional simulation, we need to choose a mesh for the simulation domain. So when one needs to choose a mesh, the first two options are whether to use a structured mesh, or the first option is whether to use a structured mesh or an unstructured mesh. In the case of a structured mesh, mesh generation is usually very easy, just especially when our domain is rectangle, so generating a tensor product mesh is immediate, but adapting such mesh is in principle almost impossible. Sorry. On the other hand, if we use an unstructured mesh, mesh generation is a complex topic, but well, solved in many existing software libraries. But adaptation of the mesh to the internal layers becomes much simpler because unstructured meshes can be locally refined without unmeshing the whole domain. Both these approaches have advantages and disadvantages. So we try to get the advantages of both without the disadvantages by using a third choice of mesh, which is hierarchically refined Cartesian meshes. So we keep the structure of a Cartesian mesh, but we locally refine it by introducing so-called hanging nodes, so that the refinement is not propagated everywhere, and so refinement can be local. So in this case, this is material with 1D fractures inside, and you can see we can refine around these fractures. And even though the mesh is Cartesian, so aligned with the Cartesian axis, the refinement regions need not be aligned themselves. We can refine along regions which are not parallel to the axis. And this particular approach presents also an efficiency sufficient to deal with moving interfaces. In this case, we see a ball which is moving in a flowing medium. So this is a Stokes equation for the flow with a ball which is bouncing, and the mesh is adapted following the surface of the ball, which is definitely not a Cartesian interface. And as I said, for the application, we're dealing with 2D simulations, but this, of course, can be applied to 3D. Otherwise, it wouldn't be of much interest. So the basis for this hierarchically refined meshes is so-called QUADTREES. Well, I assume that many people in this audience might be familiar with this topic, but I cannot give it for granted. Stop me if you find this boring. So the main advantage of using a quad-tree refinement instead of just an unstructured triangular of a tetrahedral mesh is that if we use the hierarchical refinement approach, the elements in the mesh can be represented as a tree structure where the leaves of the tree are the actual elements, and the path through the tree represents the refinement procedure. So this is another step of refinement. And using this approach, one can, a very important feature is that one can have a linear numbering of the mesh elements, even though the mesh is unstructured. And this linear numbering is can be exploited for efficiently partitioning the mesh, and this is of great interest for parallelization of the code. If the choice of the numbering is not unique, if the numbering is correctly chosen, for example, we use Morton numbering of the elements, then this partitioning guarantees locality of the partition, which is very important to guarantee reduced communication during parallel processing. So to summarize why we use this sort of meshes, which are not the most common in the finite element community, is because the mesh generation becomes very simple. Adaptation is immediate because it's hierarchical just by adding one more level in the tree. The parallel partitioning is not a problem at all because we have a linear numbering, so just divide the number of elements by the number of CPUs and you have the correct partitioning. Memory consumption is very low because all properties and topological properties of the elements in the mesh can be computed rather than stored in memory. The Cartesian representation of the elements guarantees in the discretization that we have a discrete maximum principle, and interpolation between one mesh and the refined mesh is immediate because the refinement is hierarchical. Of course, for all these advantages, we have to pay a price, and this is geometrical flexibility because, I mean, we are dealing with Cartesian meshes, so the geometry must be aligned with the axis. But as we will show in the test examples in the following, by using well-chosen discretization techniques, we can mitigate this issue in such a way that these approaches become competitive. So to explain how the discretization is performed in order to deal with the hierarchical refinement. So we start by dealing with the basing functions in the conforming mesh. So conforming mesh is one where there are no hanging nodes. And then we explain how we perform the refinement. So the refinement is, so this is a tensor product mesh. If we want to locally refine the central element of this mesh, we need to divide, always divide into 4 quadrants such element. The hanging nodes are not independent degrees of freedom. So this refinement only adds 1 more degree of freedom to our structure. And how is this done? We simply we add the new test function, and we replace the existing ones by enforcing the partition of unity property. So we enforce that the sum of all test functions remain 1. And so we add the new test function and modify the existing ones so that the partition of unity is still preserved. This approach also works when we do it the other way around. So if we have a full tensor product mesh and we want to derefine one element, we then need to remove 5 degrees of freedom, and these 5 degrees of freedom must be removed, and still we need to preserve the partition of unity. So the affected test functions, which are those related to these nodes, are modified again in order to preserve partition of unity. On conforming QUADTREES, the SCHARFETTER-GUMMEL discretization that we have shortly introduced has 2 very important features that we really care about in our application, that are nodal exactness of the solution when the equation has constant coefficients, and more importantly, that the discrete operator is an M matrix, which enforces positivity of the density of charge, which is physically and numerically very important. And also prevents spurious oscillations near interior layers. So this is for the well-known tensor product discretization, and this particular choice of the method to perform refinement and the refinement of our mesh guarantees that also on hierarchically refined non-conforming meshes, the same properties are preserved. So with this hierarchical refinement and with the Cartesian mesh, we preserve in particular the discrete maximum principles of the monotonicity of the discretization method, which is of paramount importance for this kind of simulations, where the density of charge can vary by 20 or even 40 degrees of magnitude inside the domain and in a very short distance. So I have explained until now how to deal with a locally refined mesh and possible advantages of using such locally refined mesh, which in some sense are, I agree, may be obvious. The more difficult part is how do I perform such refinement? As I explained in the introduction of the application, the location of the steep gradients is not known a priori. So the adaptation must be automatic. So the code must be able to detect the steep gradient regions automatically. So for such purpose, we used so-called recovery-based estimator. And in particular, we have this non-standard approach, which in addition to a recovery of the gradients, so the dual variables, we also have a higher order recovery of the primal variables, so the charge density and charge and electrostatic potential. So the discretization of the primal and dual variables are linear, bilinear in particular for the, no, actually the primal variable is Q1, so bilinear, and the gradient is piecewise constant on each component, and is piecewise constant in one direction and piecewise linear in the other direction. With our recovery procedure, we construct a fully bilinear approximation for the dual variable and a quadratic, b-quadratic approximation for the primal variable. And then we use an error as an error estimator, the L2, the broken L2 norm of the difference of the computed solution and its higher order recovered approximation. To make this more clear, so we assume that we have a solution U and call sigma its gradient. Then if the solution U is in the space Q1 of bilinear continuous function, then the gradient sigma will be constant. Its tangential component will be constant along the mesh edges. By using this recovery formula, we can produce instead a sigma star variable, which instead is fully bilinear. Each component is a bilinear and continuous function. Given such continuous reconstruction of the gradient, we can integrate along the edges and construct b-quadratic representation of the solution using the formulas shown here, well, which are look scary, but if you consider that to reconstruct the gradient, the function, a function on its gradient, you can just integrate it along a path, they become easier to understand. And the feature that this reconstruction formulas have is that they guarantee exactness, so that if the solution U is b-quadratic, then the reconstructed, if the exact solution is quadratic function, then the reconstructed gradient and the reconstructed numerical solution are exactly identical to the exact values. A consequence of this property is that the reconstruction of the gradient is super convergent. So even if we have a first order approximation, the sigma h computed by solving the equation is only first order convergent. Its reconstructed counterpart is actually a second order convergent. Also, this particular choice of the procedure for estimating the error has very good scalability properties in the sense that it requires very limited communication to construct this higher order convergent approximation of gradients, because we only need to cycle over first neighbors of each cell, and this will show leads to very good scalability of the parallel scalability of the method. So in addition to this, of course, we need to have a good mesh, if we have a good mesh, we can accurately and efficiently simulate our device, but we don't want the time of creating this mesh to disrupt the efficiency of the solution method. So we also developed an approach that limits the number of refinement and the refinement iterations needed to adapt the mesh by where instead of using the common solve, mark, adapt cycle, we compute a metric, which is an estimate of how much an element needs to be refined, or how much it can be refined in order to obtain the required tolerance already from the first solution of the equation. So we don't, or we have a limited number of iterations, because just with a few iterations we can compute the final target of refinement and the refinement, and using this hierarchical refinement and the refinement, we can get to the target immediately, because once we have marked the area we need to refine, we can do this without iteration. So all these methods were implemented in Beam++ with library from Politecnico. For the meshing, it is an interface to pForest. Why we built this additional layer rather than using pForest directly is because there exist many available libraries that deal with the QUADTREE meshes. I cite here just two that we had considered in the beginning. We have an initial implementation of the interface to Pablo, so we can use a different backend rather than pForest, but our first test showed that pForest is so highly efficient that we will probably later drop, tighten collaboration with the pForest team and drop the other interfaces. So this is an example of scaling performance of the method. This is on a test example data evolution. And this was an initial test where we limited to 16 CPUs, but we have fully linear scaling. We right now can deal with up to 1,000 by 1,000. So, sorry, with 1,024 CPUs with almost linear scaling in times. So now to show how the discretization and adaptation work, we consider some academic test cases. So this is a very commonly used test case for advection-dominated problems. We have an advection diffusion equation where advection is along this direction, which is skewed with respect to the domain, and the solution we have, so the boundary conditions are discontinuous, and this will develop an interior layer, an internal layer, which is aligned to this line. So here is the initial mesh, and this is how the refinement and the refinement work, and we end up with a mesh which is highly refined along the internal layer, along the boundary layer, and is very low refinement elsewhere where the solution is flat. In this example, we show how the same method can be used to deal with, well, maybe this is of interest to the Poisson-Boltzmann community. So we have discontinuous permittivity coefficient, and this is the numerical solution, which of course has a very noticeable discontinuity in the gradient. And here is the mesh that we generate, and this sort of mesh can look quite, how to say, unexpected. If you consider the geometry of the problem, one may understand why I need to refine the mesh around the interface. But indeed, what our refinement does is try to, and actually it succeeds in this attempt, to preserve the convergence rate of the finite element discretization on the full tensor product mesh. And indeed, if I want to have convergence in the tensor product mesh, I need to fully refine the mesh. So I don't get convergence if outside of the interface region I don't do any refinement. And this is counterintuitive. And so if with manually refined mesh, it would be difficult to perform such correct refinement. Of course, with this simple geometry, one might guess it, giving it a little bit of extra thought. But with more complex geometries, identifying the areas of where refinement is needed is not always intuitive. And so having automatic detection of the areas to refine is interesting. And here we have a comparison of how the error is reduced by having the error estimator approach, and as compared to refining as much as possible along the interface, which is a commonly used approach. And we see that we have a much better error, lower error with a much higher number of, much lower error with a much lower number of nodes already after a few steps in the general refinement. Finally, let's move to the actual application. And we see here a simulation of the organic thin film transistor in the equilibrium regime. So to enforce zero current, source and drain are kept to the same potential. But you see that refinement also here, well, so the source and drain are kept grounded while the gate changes bias in this example. And you see that also in this case, the refinement is not really, does not follow intuition rules, as even in the inside the insulator region, to keep the error low, some refinement is needed. And also, not all refinement is not low only at the interface where the discontinuity in the coefficient is, but also at some locations within the semiconductor where the steep gradients in the charge density are located. And we compare this approach by trying to achieve the same accuracy in the capacitance with the uniform mesh and with an adapted mesh. And just to show one case, at the highest apply voltage, we can cut the number of degrees of freedom by a factor of 4. But notice that this is the simplest case in some sense, because that's the end of the simulation where the bias is the highest, and this is the simplest possible mesh. So that's the one we could have guessed from the beginning, and probably also obtain with a full tensor product mesh. And even in that case, we can do better than intuition. So again, we see the transient simulation where we do the same simulations by changing the bias in time, and solution changes and the location of the layers moves. And please consider that these pictures are distorted. This is a thin film device where the aspect ratio is 850. So the width of this rectangle with respect to this height would be 850, which is not the case in the picture. And here are the whole simulations, and these are the currents. So let's say oops, sorry, I have. Thank you for questions. Please go ahead.
Thank you for your talk. Are there any questions from the audience? I have one myself. So you said that the refinement is not always needed where one might expect. Have you tried, for example, if you have classical, what one would think it would be a classical way to require increased accuracy, like a tip, or in more less regular geometries? Have you seen how this corresponds to the need for a refined mesh?
Yes, so of course, when you have a tip, you will have, I mean, you need, it can be proved analytically that when you have a tip, the uniform refinement will not achieve any convergence. So if you have the, for example, the Fichera corner where you have three, an L-shaped domain with a tip, standard uniform refinement will not converge. We have done similar examples in which this approach does achieve convergence. I must say that this is well known with regard to so-called Sienkiewicz-2 or recovery-based estimators. The innovation of our approach is to use these hierarchical meshes, which are easy to refine, and an estimate, a way to compute the estimator, which is very local to the CPU partition of the mesh, so that the computation of the estimator is very quick. And so the so it is well known that very locally refined meshes give very good convergence properties. Not mainstream in practice is that many times the computation of the mesh disrupts the convergence of the efficiency of the simulation. So you spend more time creating the mesh than actually solving the problem. The innovation of this approach is that the mesh is easy to refine, so it's easy to estimate the refinement, the error to refine the mesh, and to partition it again, because once you have done the refinement, the balancing between CPUs in a parallel cluster is completely changed, because if a partition is refined, then its number of degrees of freedom will increase. If it's refined, it will decrease, and so the parallel scaling will be completely disrupted if you don't repartition the mesh. And the use of this particular approach simplifies the refinement, partitioning, and balancing of the mesh in very easily measurable and strikingly efficient ways.
Okay, thank you very much. Are there any more questions? Okay, if Okay, yes, go ahead.
Maybe I have still a question concerning your performance with the parallel scalability. Since you mentioned in the last question also that the number of mesh points might increase or decrease depending on the adaptivity. So you said that the scalability would now be increased up to 1024 cores.
That's our latest test.
Yeah.
I don't know if we can go further because we haven't tested.
How many degrees of freedom do you need then to get this performance on each core?
Yeah, for this particular test, we need around like 10 million degrees, no, 10 million nodes, but then we have 3 equations, so it's about 30 million degrees of freedom. It's not a huge number, but as the problem is highly nonlinear, well, we really need to do a lot of computation. Mm-hmm. So the computation, even if the number is not, I mean, I know of much higher simulation with much higher number of degrees of freedom, but the nonlinearity in this case is, and also the time stepping. I haven't discussed this topic, but the time scale of the simulations can be down to the picosecond. Mm-hmm. And so simulating milliseconds or seconds is non-trivial. Mm-hmm. So even just 30 million of nodes requires a lot of computation.
How would you estimate the overhead for the repartitioning after?
We measured that in our case to less than 1%. Mm-hmm. So the time needed for partition is always less than 1% of the total simulation time.
Okay, thank you.
And that's for the repartitioning. The repartitioning is actually, repartitioning is unmeasurably slow, fast. That includes the remeshing. Mm-hmm. But also in this case, it's not complicated, so it's expected to be fast.
Okay. Any more questions? I don't see anybody raising his hand. So let me thank again the second speaker of today, Professor De Falco, and all the audience. I remind people that the presentation of today have been recorded and streamed on YouTube Protein Electrostatic channel. The next meeting will be next Wednesday, September 8th, with the speakers being Giuseppe Milano and John Herbert. I thank you, everybody. I thank everybody, and see you next week.